Hey AP, today we are going to be talking about the equations of motion. What do I mean by this? Well, we can use all those kinematic equations in a useful way to describe how an object moves. So like take this graph for instance. Does the kinematic equation accurately predict the motion of the object? We have this kinematic equation that Vx equals our initial velocity times the acceleration times time. Well, do I have this information from this graph here? Well, this tells me that my initial velocity, Vx naught, is equal to 0. It also tells me what my slope of this graph is. Ax is just going to be my slope, which in this case I could take any of them. It's just going to be 4 meters per second squared. And then does the line, like think about in terms of y equals mx plus b, does this kind of make sense here? Where I have I'm making an equation for v, a function for time. I can plug in different t's and it will shoot me out different v's. And my function for time then would look something like 4t plus 0. And now I have a function like that I could plug in anytime. Let's say I want to know what v sub 4 is. Well, if I plugged into this equation, I would do 4 times 4 plus 0, which just equals 16. Do I get that answer out? I do. That if I plug in 4, I get an answer of 16. This is what we would call an equation of motion. It's an equation that describes the motion of an object, and it kind of connects back to an inherent kinematic equation. And we can use the fact that this, like how an equation looks, to kind of figure out what some of its variables what more specific values would be for its motion. Let's see this again. If we wanted to make an equation that described the line, we just talked about this was y equals b plus mx, and like our slope here we know as our a, our y is our x is here, and our b is our initial y velocity. The equations that relate to motion are called equations of motion. For an object accelerating at a constant rate, we expect a linear VT graph. So we know this is the VT graph that I see. Well, in between A and B, like we have a nice linear change, so we know the slope is constant, and so our acceleration should be constant. And then we can form, so if you may be asked, like from a graph, determine the equation of motion from this. Well, we know, like we're trying to just figure out like a y equals mx plus b kind of situation here. Well, our initial velocity is 30. Our slope here, we change 30 in 3 seconds. That's an acceleration of negative 10 meters per second. We'll even call this a Vx naught of 30. So what would my equation of motion be for this? Oh, I could call it, I'm going to do the same as what I did. V sub t. This is just saying I have velocity, which is a function of time. Kind of is indicating my v is my y and my t is my x. And then this equation would be at, and my a is negative 10, times t plus 30. And again, you think about it however which way that we wanted to. My final velocity is like the function, the y. My b and my a is just my m, and we end up with an equation that looks like this. Now this equation, what if I did the opposite? What if you just started with this equation? I asked you, well, just from this equation of motion by itself, what is my acceleration? Well, we can see whatever's paired with the t is going to be the acceleration. What's your initial velocity? Well, whatever's standing by itself is the initial velocity. So we can gain information from a graph to make an equation of motion, or we can have an equation of motion and turn it into a graph. What would we expect for a position time graph? Well, thinking of position and how we could define it, well, we do have part of an equation for position. This is our kinematic equation. We're missing a little bit here, aren't we? Plus 1/2 ax t squared. Well, if we have no acceleration, well, then we can just use the first part of this equation to define our position, which is exactly what we're going to do here. And do we get a similar equation of motion understanding of this graph? Well, we do. We can see that we start at an initial position x naught is equal to 5. And our slope now of this graph, our m, is going to be completely proportional to our velocity. And we now just have one velocity, just vx naught, because it's not changing with no acceleration. We just have a linear change in position over time. And so what if we do have acceleration, though? Well, now we're going to need that other term that we ignored last time. And really, we're just fitting this to a simple quadratic equation where our constant is still our initial x position. Our whatever's with our t ends up being our slope, or our initial velocity, which is our initial slope to start out with, and then whatever's with our x squared, or in this case our t squared, is half of our acceleration. This half is very important for when we're trying to mix and match to figure out what the acceleration is. So let's see an example of how we might use equations of motion to help us understand problems or figure out equations of motion. So what would the equation of motion be for this VT graph? Well, we want an equation that describes velocity as a function of time, right? And there's really just one equation. Well, there's two. We could either have essentially, think of our three kinematic equations that we have. We are always going to want an equation of motion to be with respect to time. And so that's going to leave me with two options. Vx equals Vx naught plus axt, or we are going to have x is equal to 1/2 x naught plus v naught t plus 1/2 a t squared. These are our two equations that we're going to be using because we are going to want a v sub t with respect to time. Our other equation does not have time in it, and we are not going to use it as an equation of motion. So how could I express which equation am I going to want to use? Well, this is a velocity versus time graph, so I'm going to want velocity here. So I can just say that this is equal to Vx naught plus axt. What are our values here? Do I know Vx naught and do I know ax? T just stays t. Well, I do know. I know my initial velocity is 30. Do I know what my acceleration is? Well, what's my slope here? What's my change in velocity? Well, I can calculate for the first few seconds. We have a slope of, we go down 30 in 3 seconds. And so our acceleration is 30 minus acceleration is 3t. Right there, we have an equation of motion. We should ask ourselves, is this going to change at any point? Is it constantly the 30 minus 3t? Well, it does kind of change over here because our slope no longer becomes positive 30 or negative 3, but we switch to increasing our slope rather than decreasing it. So we would have a separate equation of motion. So for this part, probably call that Vt equals negative 30 plus 3t to switch those two. That would be the equation of motion, though. An equation of motion for a car is given by the equation Vx equals 2t minus 5. What's the initial velocity of the car? Easy, negative 5. Vx naught equals negative 5. What's the acceleration of this car? Well, what's with the 2? A is equal to 2. Remember, what are we pairing this equation with? This equation is based on whatever's with the t is going to be ax times t, and then plus Vx naught is just rearranged equation. So the Vx naught is negative 5. What is the velocity of the car after 12 seconds? All we got to do is plug it in now. Literally just plug in 12 there and we'd get an answer, and we'd get 6 or 2 times 12 minus 5 because it would be 24 minus 5, and we get 19. The velocity is 19. What is the displacement of the car after 12 seconds? Well, now, do I have a displacement? Well, let's take a think about what we do know. We know our initial velocity, Vx naught, is equal to negative 5. We know our acceleration is a positive 2. We know that we are doing this for 12 seconds, and we want to know what is the acceleration. Yeah, we can even say we know our final velocity after 12 is 19. Well, this equation is not going to help us find the displacement, but certainly another equation could. And in this case, we could use either. X equals x naught Vx naught t plus 1/2 a t squared. We could use this equation, or we could use Vf squared equals or sorry, not VF, Vx squared, Vx naught, 2a delta x. Either of these equations will work. You can use either of them. Actually, why don't you guys test that? See if you can use both of them to get the same answer. You will have to do different math either way, but they should yield the same answer regardless. All right, let's see. This equation of motion of a biker is 40 minus 2t plus 0.2t squared. Remember, we are fitting this to one of our equations. We should always be able to start out, what equation are we fitting this to? Vx naught t plus 1/2 a t squared. And then just look to see, I mean, we got, in both cases, something with a t and something with a t squared. And then what are those things that are paired? So I have 1/2 a is 0.2. I have Vx is -2. Do the whole thing. -2. Negative is important there. And I have an x naught equals 40. And just from this alone, that can allow me to just go through and make, well, I know x naught must be 40. I know Vx naught must be -2. I don't know that a is 0.02, but I know that half of a is 0.2. So let's figure these things out. What's the initial position? Know it. It's 40. What's my initial speed? -2 meters per second. What's my initial acceleration? I have to just take one step. If half of a is 0.2, what's a? A is equal to 0.4. We just got to double it. What's the position after 20 seconds? All you got to do is take your 20 and plug it into the formula. This equation will literally give you the position given a certain time, and just plug in 20 there and you will know it. What's the velocity after 20 seconds? Here we're going to have to switch to a new equation. We're going to need to switch over to this equation here. And we can easily do that because we know what our initial, we know this is 40. We know this is -2. We know the acceleration is 0.4. We know the time is 20, and we can figure out what the velocity is then after those amount of time. So you got to plug in the right things. So go ahead and try that out, see what you get. All right. That is pretty much equations of motion. I'm going to leave you with this problem, and I'm not going to walk you through how to do it, but see if you can figure out what this is going to look like. Man's on the top of a cliff. He's dropping things down. Think critically about what would a velocity versus time graph look like? What would a position versus time graph look like? Can we get equations of motions for PT, for the position as a function of time and the velocity as a function of time for this situation? Best of luck on working on this. As with anything, always let me know if you have questions, and I'm happy to help.